Today's lesson is on logarithms. Logarithms, or logs, are the inverse of exponential functions. As such, they will follow the same rules as exponents. Every function in exponential form can also be written in logarithmic form. If we look at the first function in exponential form, we have x equals a to the y, or the result equals the base raised to the exponent. The same problem written in logarithmic form looks like this. The exponent equals the log base a, and it's read as base a, of x, and x was our original result. And you need to be able to write these in both directions. So if you look at our first example, we had 25 equaled 125 to the 2/3. So my exponent was 2/3. That came first. And that equaled the log to the base of 125, and the result was 25. So 2/3 equaled log base 125 of 25. Now, the next problem is also set up in exponential form, 9 to the 3/2. Everyone try to write that one in logarithmic form. I hope you came up with 2 for the exponent equals the log base 3 of 9. I kind of look at them this way. 3 to the second equals 9. It makes a little circle there. Now, I have some problems that are in log form, and I would like you to rewrite them in exponential form. Try them, and then check it out, and then try the other 2 sets of practice problems there, and see how you did. Pause the podcast, and then check your results. Hopefully you came up with these results. Now we need to be able to evaluate logarithmic expressions. The steps are: 1. Change to exponential form, 2. Get both sides to have the same base, and then 3. Solve the exponential equation. By the exponential equation, I mean the equation set up just by the exponents. In our example, first we'll start by rewriting log base 625 equals x in exponential form. So I get 5 to the x equals 625. The next step is to get both sides to have the same base, and I know that 625 is some power of 5. So if I factor 625, it's 25 times 25, or 5 times 5 times 5 times 5, so I can rewrite that as 5 to the 4th power. Now, when I said solve the exponential equation, I meant just look at the exponents. So our result is x equals 4. Now let's take a look at our second example. How long would it take for 256,000 grams of thorium-234 with a half-life of 25 days to decay to 1,000 grams? First off, this is an exponential decay problem, so we're going to use the exponential decay formula. N equals n sub 0 times 1 plus r to the t. We're going to start with n is 1,000 grams. N sub 0 is 256,000 grams. Remember, n is the final result. N sub 0 is what we have originally. And in this case, r is negative 1/2 because it is losing half of the amount. So, t is going to be the number of half-lives, because time and rate have to be related. As we start this problem, we'll simply substitute the numbers in to what we know we have. 1,000 equals 256,000 times 1 plus negative 1/2 to the t. Now I'm going to work within the parentheses, and 1 minus 1/2 is 1/2. And then I need to isolate the exponential part of this equation. I need to get the 1/2 to the t power alone. So I divide both sides by 256,000, and when I do, I get 1 over 256. At this point, I need to get that down to the same base, so I want it to be in terms of halves. So that means my 256 needs to be broken up into powers of 2. So let's start with that. If I have 256, that's 16 times 16, which is 4 times 4, and 4 times 4, which is 2, 2, 2, 2, 2, 2, and 2, and 2, or 1/2 to the 1, 2, 3, 4, 5, 6, 7, 8th power. You'll notice I wrote it in logarithmic form. Then I figured out that that was 1/2 to the 8th power, or 1/2 to the t equaled 1/2 to the 8th when I went back to exponential form. These two steps in here are not necessary. It's just sometimes seen that way. I could have skipped straight from 1 over 256 to 1/2 to the 8th. And then I can see that my exponents are the same, so t was 8, which meant there were 8 half-lives. Each half-life was 25 days, so it was a grand total of 200 days. Now, take some time, pause the recording, and try the next few problems. One thing to remember is, since they both involve fractions, the exponents will be negative because those are the reciprocals of the bases, the base of 2 and the base of 10. The first problem was a little bit more straightforward than the second problem. We simply had to change 1/2 into 2 to the negative first power and then multiply the exponents, so x was equal to -4. The second problem was a little bit trickier because you do need to change the decimal into a fraction first. It just makes it a little bit easier. Now we're going to look at some rules of logarithms. The rules of logarithms are the same rules as products, quotients, and powers for exponents. For example, when you multiply two things of the same base with their exponents, in other words, b to the m times b to the n, you get b to the m plus n. Remember the addition, and we started with a multiplication. If we have the log base b of mn, then it breaks down to the log base b of m plus the log base b of n. We're going to use these properties to make solving some problems a little bit easier later on. Similarly, with quotients, the log of m over n is the same as the log of m minus the log of n. Remember, you subtracted the exponents when you were dealing with division problems in exponents. And the power rule is probably the most important one because remember you multiplied the power. Well, in this case our power is going to drop in front and multiply the log, and that gets used a lot. Specifically, you'll use it a lot in calculus. Now the last one is more of an inspection rule. If you can see that they both have the same base, everything is the same except the m and the n, then you know that m equals n, and that is the equality rule. Now, let's go ahead and solve some problems with it. We're going to use the properties of logs to make it a little bit more workable. We're starting with 15/625 log base p of 15/625 to the 1/6 equals -1/3. So the first thing I did was I rewrote the problem using exponential form. So I had p to the -1/3 equals 15/625 to the 1/6. At that point, I factored 15/625. You could use the exponent function on your calculator. Just do 15/625 to the 1/6 power. And when I did, I ended up with 5 to the 6th to the 1/6, or 5 from the calculator. So I have p to the -1/3 equals 5. Now at this point, I needed to raise it to the reciprocal power to solve for p, so I raised both sides to the negative third power. And when I did that, I ended up with p equaled 1 over 125. Now let's look at some other problems. It just takes some time and practice to recognize which properties you're going to be using. Notice on this one the logs were the same, so I was able to just basically cancel them off. It's the equality property. So what I had was 2x plus 5 equaled 5x minus 4. Simple equation, subtract 2x, add 4, get 9 equals 3x, divide by 3, and x was equal to 3. The next problem, you can see the subtraction here, so that meant that it involved a quotient property. So the first thing I did was I rewrote that as a quotient. So I had the log base 3 of 4x plus 5 over 3 minus 2x. Then by using the definition of logarithm, or rewriting it in exponential form, I had 3 squared equals 4x plus 5 over 3 minus 2x. It's starting to look a little bit more doable now. Got 9 equaled 4x plus 5 over 3 minus 2x. Solved my proportion, did my cross products, multiplied. Remember, that's 9 over 1. Multiplied, and ended up with 9 times 3 minus 2x equaled 4x plus 5. Solved the resulting equation. 27 minus 18x equaled 4x plus 5. Ended up with 22 equals 22x, so x was 1. Here are some problems for you to practice. You will be using all the different properties of logs in these. Give it a try and then check your results. I've written the property that I used next to each line where I used one of the properties of logarithms. Probably the most interesting one is the fourth problem, where the power rule comes into play. And then the quotient rule comes into play, which made the problem actually a fairly easy problem. To graph logarithmic functions, what we want to do is we want to rewrite the problem in exponential form, but then instead of choosing values for x, we're going to choose values for y and simply solve. So you'll see in our example, I started with y equaled the log base 2 of x minus 1. So 2 to the y equaled x minus 1. So that gave me 2 to the y plus 1 was equal to x. Notice I solved for x. Now, these problems cannot be done on your calculator because they are not base 10. The log key on your calculator is everything done in base 10. So I'm simply going to set up an xy table, and I'm going to set values for y. So first I'm going to pick negative 2. So that's 2 to the negative 2 plus 1. That's 1/4 plus 1 is 1.25. So my x value is 1.25. When I do to the negative first power, I get 1/2 plus 1, which is 1.5. When I do the 0 power, I get 1 plus 1, which is 2. When I do the first power, I get 2 plus 1, which is 3. And when I do the second power, I get 4 plus 1, which is 5. So this is what my graph looks like. 1.25, just a little bit more than 1, negative 2, 1.5, negative 1, 2, 0, 3, 1, and 5, 2. Now, if you remember anything from the earlier chapter, which I hope you do, and you think of exponential functions, remember an exponential function would have looked something like this. And this one is actually the reflection over the line y equals x, which is what all of our inverse functions do. They reflect over the line y equals x. So now, this concludes today's podcast.